works. Right, okay. So, in today's session, we're going to have a look at. Hi, guys. Now we're recording, so let's focus on that for a moment, shall we? Year 7. Right, so what we're doing is looking at terminal velocity. All right. Now, what I'm going to try to do, it's something you've got to understand. There's lots of things we've built to get there. So I'm going to look at what we've got 1, 2, 3, 4, 5, 6, 7 keywords. Your job is solely to understand those 7 keywords. Right? Some of you will. Some of you will find it quite difficult. But that's just how you've come across, science. So let's start, shall we? Okay, so keywords, weight. Now, this is the first thing, and I hope over the past several months I've been quite clear about this. This is weight in physics, not weight in English. So this is not kilograms. This is the force acting on an object due to gravity. And it is a force, and the units of force is N for newtons. Drag. So to me, when people talk about drag, the thing that I think about is air resistance, all right? And I love biking, I love mountain biking, and the faster you go, the more the air pushes against you. That's air resistance. Now, there's a word that I think I've used twice, and you're not going to remember it, is fluid. And most people think about fluid, and we talk about fluids as liquids. But actually, it's anything that can move, can flow. So one thing that's included in fluids is not just liquids, but also gases. And as I said, this is not English, this is physics, and you've got to understand it. Now, resultant force, and we've done this, but I'm going to show you again, and I'm going to show you in terms of what we need to understand. If I have a ball and I drop it, its weight is downwards. All right. Let's say it has a weight of 10 newtons. Right? Remember, this is not kilograms, 10 newtons. And if the air resistance in the opposite direction is 5 newtons, then the resultant force, but the resultant one, will be 10 minus 5 to give me 5 newtons. That is the resultant force. I don't want to think about, so what a lot of people do is they see images like this and they get really confused. There's so many arrows, but actually I'm not interested. So if this is 10 newtons to the left, this is 10 newtons to the right, this disappears. The resultant force, left and right, is gone. And the only thing I need to know is I've got a resultant force down of 5 newtons. All right, that's a resultant force. Acceleration we looked at last week, it is changing speed. It either increases its speed or decreases. Terminal velocity. So if you look at the world's fastest car, it reaches a maximum speed and it cannot go faster, right? And the reason it can't go faster is because the force due to air resistance is the same. Right? Balanced forces. When upwards, in this case, when we look at terminal velocity, we're looking at dropping things. It's when the upwards and downward forces are equal in size. So if I draw balanced forces when it comes to terminal velocity, if this is 10 newtons and upwards air resistance is 10 newtons, my forces cancel out. My resultant force is 10 minus 10. It's 0. So when your resultant force is 0 newtons, this is what we call balanced forces. Your object isn't getting faster, it isn't getting slower. All right. This is really interesting one, falling in a vacuum. So we are so used to living on Earth with an atmosphere that we don't realize the reason why things fall at different speeds or different velocities is because of air resistance. And a few years before I was born, humans had gone to the moon. and even during the time I was born. And I remember very clearly this. So they're on the moon. And like if I said to you on Earth, if I drop a hammer, which one, and a feather, which one hits the ground first, which one moves the fastest, you go, right, it's the hammer. So they went to the moon and did the same thing, and both fell at the same speed. They hit the ground at the same time. All right, their acceleration was the same. You don't have to go to the moon to that. You can do it in a vacuum chamber for human experiments. So you can do it. You can literally get a vacuum chamber and do experiments. And there are some very, very, very big ones. And the world's largest vacuum chamber, if you look at it, where we can do experiments, looks like this. And irrelevant to the object, whether it's a feather, the same thing, or a hammer, it will drop down at the same acceleration and they will hit the ground at the same time. So it's a huge vacuum chamber and you actually go in and do experiments. But you can't go in like this. You would die, right? There is no air to breathe. So you'd need something like a spacesuit in there. You can't just go in there, which is really cool. All right. Now, so that's falling in a vacuum. Without air, objects accelerate at the same rate, regardless of mass, because there is no air resistance, there's no drag. Falling in air, as an object falls, it hits air particles, and they push it upwards. That's what we call air resistance, or drag. Now, the speed factor, the faster you go, the greater the drag. The faster you go, the greater the air resistance, all right? Because more air particles are going to smack it. Now, reaching terminal velocity. This happens where this diagram I've drawn, if something is dropping and its weight is 10 newtons, and air resistance is 10 newtons, that's it. It's reached its maximum velocity. That's what we call it terminal velocity, all right? Now, resultant force has to be 0 newtons if you've reached terminal velocity. If you have the resultant force, you are changing speed. In this case, you are getting faster. All right. Now, there are two formulas you need to know. I've done one of them before, but I'm just going to go through it again. Weight equals your mass in kilograms times gravity. Gravity on Earth, unless we tell you otherwise, is 9.8. So when you look at my weight on Earth, my mass is 100 kilograms. Gravity is 9.8. Let me just move that up. Oh, I'm going to sneeze and it's not going to be. It's tickling. Oh. Let's just undo that. Hit this, lock this, select that, and let's just move it up. All right, so if you look at my weight is mass in kilograms times G, which on Earth is 9.8 newtons. That should say 9.8. 100 times 9.8 equals 980 newtons. This is my weight in physics. All right. Okie dokie, 10 easy ones. You have to read that again. One of the biggest issues with students, I don't care if you're year 7, I don't care if you're year 13, you read it once and think, I know it. No, you don't. All right. Anyway, that's a very, very long